Hello, welcome to this recording on midterm examination, the model question paper. This is for the course Operating Systems and System Software, where basic operating system theory is taught during the 3 hours and lots of programming using C as well as pthread libraries as well as system calls of Linux is written during the lab hours. Now, this is going to be the first part of the recording. Let us look at the questions, and I would be maybe solving 5 questions here in this lecture. Okay, let us get into the question first. Whether the given statement below is true or false, justify your answer. Context switch between the threads of the same process is faster and easier. So let us first recap on what is a process and what are threads created by the process. Now, a process is a program which is an executable that you run it on the system. When I say we run on a system, we bring in the resident set of the program or executable into the main memory and make the CPU run that. Now, how do we control the CPU, or how do we make the CPU to start executing the program? We know in C, main is the entry point of the program. So we give the code area, whichever address the particular main function is located, we give that address to the program counter of the PC, and then it starts picking up the instructions from there and starts executing, and it runs the program. Now, it's not that easy that you can just make this program executable and run it, because the OS is not there to run only your executable in the system. It has got many other jobs to do. Apart from its own system processes, it needs to take care of any interrupts, timer or hard disk or network interrupt, anything coming into the system. It has to support it, it has to process it. So any program that you write cannot be run in isolation. They need to be running along with the rest of the system, rest of the operating system. So what happens in a real scenario is, we have the main memory, which is normally 4 GB or 8 GB. OS has been already loaded into the main memory, which is residing in the main memory, and which is also having a control on what is happening in the system. Now, when we bring in our executable, it is one of the programs running there. For that purpose, we need to make sure that any executable, either we write a hello world program, or maybe we run a PowerPoint or a acro read or any video recording or anything that we do, they're all first of all run as a process. The reason that we bring in the process concept into the operating system is they run as an independent unit along with the rest of the processes in the system. How can we make it independent? That is the job of OS, to make sure that every process in the system is getting the control of the CPU, because if it has to run, it should be executing on the CPU. That means it should take control of the CPU. Now, how do we give the control of the CPU? OS schedules a process onto the CPU, and will it be only uh, kept in the CPU till the process says that okay, I am done with it? If that is the case, then it's called non-preemptive. That means the OS does not come into the picture at all until the process stops, and then it says that I have done my job. Then OS comes and then schedule something else. But that is not practically possible to make one process occupy the CPU until it wishes to give it up, because then the system can become non-responsive, because you can even say a while one, which is in C, means as a infinite loop. Then your process can hog the CPU forever. Then nothing else can happen in the system and the whole thing can crash. So normally OS has a control on what is happening. It keeps a tab on what are the interrupts coming in, and it services them. So effectively, a process is one which is a single unit of an executable along with its own components like code, data, and stack, then heap. Now, what are these? They are all called segments, different segments. Code segment is to keep all your programs that you have written, anything that can be executed in a C language instruction are all part of the code. Any function definitions or even the main function, whatever you write. Now, what is data? Data is any variable that you declare. It could be all global or static data within the function. You may have a function, and then inside that you may have a static int I. We say that this variable exists or lives throughout the program. That means that this variable, whatever we declare as a static, doesn't reside inside the stack, which is, though it is defined inside the function, it resides in the data area, because stack is coming up, going off whenever the function is called. So you cannot keep a static variable there and expect it to hold the value that was earlier held in that variable. So it needs to be in data area, but it is for all practical purposes within the function, only to give the scope of access of this variable only to the instructions within this function. So effectively what we are saying is the data is going to be in the data area, which is also part of the main memory. Then stack is going to be increasing or decreasing based on the function calls. If you are having a recursive function call, then you may have stack growing up continuously. And heap is whenever you use malloc or any libraries that you use, then we will malloc is library for dynamically allocating memory, which will be used in the heap with all the memory allocated is part of the heap. So this is a summary of what is a process. If a process needs to run in the system, they need to have all these components, because we will have different components of data, code, stack in a program, and all of them need to be there. Now, one thing we need to remember that we don't need all the entire data or stack that you have in your program at the same time. The reason being, the program what is running in the CPU is not accessing every code that is written for the program, or it is not accessing every data array or every data that is there in the system. It is going to be operating on a small part of the code. Based on that code what is being executed, it is going to access the data related to it. So we can bring in from the hard disk whatever we need into the main memory and then run it. So this is called locality of reference, which is the main concept in software engineering, which helps us to achieve, even if we have a limited main memory, and the CPU can still run the entire program, even if it is bigger than the requirement of memory, code, or data area required for the program is much larger than the main memory, it can still run on the system. So having understood what is a process and what is the need for it, now let us understand the question here. What is a thread? Now, when I say process, it has got code, of course, I told you, and data. Then it also has a stack. Now, when we have a main program that you are executing, it is a process is created. Now, there are many library functions. We will be using pthread create, a library which will be explained shortly as we go further into the question, solving the question paper. So pthread create is a one function call which is part of the pthread library. P is for POSIX, Portable Operating System Interface. Okay. Now, when we create a thread, what happens is there is a program which is going to be run in parallel to the process. Now, when the main starts running, it's called a main thread. Okay. Now, it has got its own data stack. Let me picturize it like D here, and its own stack, and then maybe it also has a heap. Now this is the process area. Okay. Now code, I messed out the code, so let us give this entire space for code. Now I said that we are going to create a new thread. Now this thread, whatever we create, is going to run in the context of, let me call this as a main thread M1, or MT maybe I'll call main thread, because anything, a sequence of execution is a thread. So even if the process is huge in terms of its size because of the data stack and heap, of course, any process with a lots of code in it, it will have a code area also bigger. So this is larger in shape, so process is there. and then we create a thread. Now for thread to run, we need to give an entry point because we had a entry point well defined as per the language. It could be anything. Right here, as per the C language, main is the entry point. So we know what is to be executed once the OS says that okay, now I have done everything ready for you, start running. Now you should give the code for the CPU to start running. So that is the entry point, which is main. But now when you are creating a thread, you are saying that I want to run another piece of software, a sequences of instructions. Now that sequence of instructions need to be given. That is what we give it as a part of the pthread create, a thread function. Now what is thread function is an entry point to the thread. That means that function will be executing when the thread is once thread is alive and starts running. Now let me give a um, this is the signature of that function. That means it will accept a parameter which is a void star. I will explain that later on when the context, during the context, when it we discuss about it, and return some result. Why do we need this? First of all, we need a process wants to start off something which needs to be run in parallel to the main thread. That means you want to make use of multi-core processes which are there in the system, and then you want to parallelize as much as possible. Many tasks that could be parallelized can be siphoned off as an individual threads, and that can be run in parallel. So that's the intent why we create threads. Now once we get a thread, it's not enough if you just say that this is the entry point. Always any program needs to be given a data, otherwise it doesn't know what to operate on. Similarly, after the data is given, then it will be processed, then some result has to be returned by the thread function. So that main can actually this can spin off different threads to make it run in parallel and then get all the results from them to process them. So we need to have a mechanism of having a return value coming from the thread function. So that's the reason this generic library, which is a thread function, is given as a void star as an input and then another void star as an output. Why void star? Because anything can be sent as a void star. Any structure or a big data area can be given as a void star, and you can create that structure and give it out. Now you may have one thinking in your mind, how will this thread which is running in parallel can access the void star pointer which is passed by the process? That is a thing which we need to understand. The thread that is running in the context of process has access to the code and data area of the main process. So it will have access to the data and code. That means any data that it has defined can be passed on to the thread, and while the main thread is also running, the other threads can also run in parallel accessing the data. Only thing is we need to make sure that the data which is being accessed parallelly by these multiple threads, we should avoid any mismatch or anything corrupting getting corrupted. We need to take care that mechanism we will learn in the later part of the course. Here you need to know that it can have access to the data, and it will be executing the code which is part of this executable. So job is done. Now we have the thread created, and it's not that only one thread can be created, multiple threads can be created. Now the question what we have in the first part A is context switch between the threads of the same process is faster. Now, what is context switch? When I have multiple CPU cores and then I want to maybe main one is running here, the main thread, sorry, main T. T1 is running, maybe T2 also I have created, that is also running, and T3 is here, that I have a quad core processor, they are all running. Now, I have created another thread, maybe T4. Now, I want to switch between T3 and I want to take away T3 and bring in T4. Now, where do they reside? They all reside in the same main memory. Okay. They only the threads will have its own stack area. It only I can say ST1, stack of T1, stack of T2. They will have different memories. It's not part of the process memory. But any code is executing from here, and any data it is accessing from here, and it will have only its local variables which are well defined within the function. So because of this, what we need to do while we context switch means when you take away some a program which is running on the CPU, we need to make sure that all the registers within the CPU, whatever is the content, whatever R0, R1, R2, or any other registers which are there in the CPU, they need to be saved. That you know that in operating system there is a process control block which is used for saving them. So apart from that, we need to make sure that the stack is safe. We will not be saving it in the hard disk until we want this area of the stack which is in the main memory to be swapped out. Otherwise, normally we were not saving it in the part of the process control block. Process control block is a maybe a 1 kilobyte of area or maybe a little more, but it has got all the information about process, its priority, and register contents of the CPU when the process was last running on the CPU. Only those contents are there, and any files it has opened, file descriptors, and any IO it has initiated, those information will be kept in PCB, but actual code data and stack will not be part of the PCB. They are all on the main memory, but any references to them is there part of the PCB, so that OS knows what are the relevant details related to a particular process which is in the main memory. In case if it has to bring one process, if it has to move one process out and the entire process out of the main memory, it will be able to do it and then make sure that the PCB which is in the OS area is capturing that information, and where exactly it is in the hard disk also will be taken care of. So effectively what I am saying is, when we want to switch between two threads of the same process, we need to only save the register content, and then stack will be there in the main memory, but stack pointer anyway will be different for different threads, so we can easily swap in, or we can context switch can be done by moving the T3 out, saving that in the PCB content, PCB part of the PCB, and then bringing that T4. Now you may wonder, how do I have PCB entries? Each of those process as well as the main other threads individually, they have different PCB entries. They also have a PIDs. So you can save it in their own PIDs, and there will be a reference to the parent thread which is has created this thread. So there is that entire data and sequence of information is maintained inside the OS, which is part of the pthread library, which is taking care of that with the help of the OS. Now, because of this will be faster. Now, what will be slower? Now, imagine you need to bring another process. Okay, MT is one process. This T1 is also belonging to this process. Now, if I am moving T1 out, which is part of this MT, and I am bringing some other P3 process into the same core, in that case, what happens is you need to not only save the register content and stack area, we also make sure that in case we need to bring another process into the CPU, you have to make sure that the process is first of all in the main memory. That means the entire process has to be maybe switched into the main memory, and then we need to swap them. So any context switch between processes belonging to, or bringing two different processes into the CPU is time consuming, or two threads which are part of another process will also be time consuming, because entire cache line will be refreshed. A lot many things are happening there, but I will not go into the details of the hardware. But one thing you have to remember, that this is context switch between threads of the same process will be faster. Now I think this entire uh, over, overview of the entire thing will be useful to have a context as well as to understand the rest of the recording about the questions. Now, give one possible reason for a process which is currently in the blocked queue to get moved into a ready queue. Now, I need to talk about little bit about states. Now, any process in the system will also have its own state maintained in the PCB entry, okay, process control block entry. Now, what is the state? It will be new state when it is started off, and then it will go into the ready state when the process resident set is moved into the main memory and only the CPU is required for it to run. And then now, when the CPU is executing a process, based on the code that you have written, maybe you have written a f open, then you are trying to open a file. Now this is not going to be easy job, because you need the help of hard disk, or wherever you have stored your file, even SSD, you need to access it using the device driver. Now accessing the secondary devices, storage devices, are slower compared to accessing the main memory or even the speed at which the CPU is running. So F open is not going to happen in a short time. So there is no point in making this process to occupy the CPU till the F open is completed and the entire file is moved to the main memory. Now when I say file is moved, remember that the exact content of the file is copied here. Every byte is copied here. Okay, need not be the entire file, maybe whatever file pointer is pointing at, okay, at read pointer or whatever you are trying to read, a part of the database or anything, that is only brought into the main memory, a part of it. It's not that only one byte you bring maybe a 4 kilobytes or 8 kilobytes of file into the main memory, and then you wake up the process to run on the CPU. Now till that point, when the device driver is busy accessing the hard disk and then bringing the file and to the main memory, we can actually make use of the CPU for running some other process in the system. As I told you, any system with a OS is for time sharing the different users and different processes belonging to the users, or it may be different processes run by the same user in a desktop environment. So a process which is in running state can call any file open or any key entry. You want to wait for some key being pressed by the user, which you don't know how long it is going to take. So we, as the OS, what it does, it moves that process as soon as it is asking for some input from any other device, external device, or a file, or from the keyboard. It is moved into a blocked state, because OS should remember that what is the state of the process, so that it can bring back when that event happens. Now what is that? When will it be brought back from the blocked state to the ready state? Because it cannot be brought into the running state, because some other process may be running in the CPU. So from the from the blocked state, it is brought into the ready state. Okay, you can refer to any material that talks about the transition of the different states. But from block state, it is brought into the ready state. Then it will be going to the CPU when the scheduler picks up this process to run on the system or the CPU. Okay, so these are the things. I give one possible reason for a process which is currently in the block queue. I'll be giving the short answers at the end, which will be useful for people to understand how to answer one more questions. But explanation is given at length, need not be written. All these things you don't have to write, but the explanation is for to making sure that you understand the concept, as well as you are ready for any interviews or any other uh, questions you come across related to this. So blocked queue, now currently in the blocked queue, is getting moved into the ready queue. That will happen only when a process has initiated some IO request, which has happened now, and it is now whatever file we wanted, it is opened and it is ready. Then it will be brought into the ready state, and then the scheduler will be picking it up for running it on the system. Now, having understood all this, let us now try to understand about schedulers. Now, as I mentioned, a scheduler is a unit, a module of OS, which is picking up what are the ready processes there in the system, which one is to be run. See, remember when I say one CPU, we only concentrate on one core. If there are multiple cores inside the processor, then the scheduler algorithm will be running for each of the cores to pick up one. It's like you can imagine the same thing is happening 4 times. But let us limit ourselves to a discussion where one core is there, and then we are looking for a particular process to be picked up. Now this is a Gantt chart, okay, which is showing you how the different sequences of processes are running in the system. Now, arrival time is the time at which the processes have become ready. It's not arrival time. This not doesn't mean that it's a new state. It's a time when it can be picked up for running on the CPU. So whatever is shown here, 0 to 3 means the time unit 0 to 3, the process is running on the CPU. That means it came into this only when it was ready prior to 0. Okay, now P1 and P2 have become ready. Then the scheduler can decide when two processes come at the same time, it can pick up based on the PID of the process. Now if I call this 1 as a PID and 2 as a PID, then you can have an algorithm that we always give a lower PID for the process which has come into the system, or which has been considered or recognized by the OS first. So P1 is the candidate to be picked up when two processes are ready at the same time. So P1 is picked up. Now it says that it is running for 3 and 12 and 15. Now we can see that the time gap is not equal. Okay, 3 to 12 is a longer duration, right? Then we have 9. Okay, we have how many time units we have? Okay, 3 units of year, and this unit is much more than this, and this is again 3, this is 3, then this is again 6. That means it's not based on the time unit, quantum time. That means the scheduler is not getting interrupted at regular interval. Then most likely, okay, you can put all your assumptions. You don't have to ask anyone, assuming that this is a non-preemptive scheduler, because there is no fixed quantum here. Okay, in case the questions come up about what kind of scheduler is running given this sequence of processes, okay, or what kind of scheduler algorithm is being used, so you need to have a justification for anything that you write, and any assumptions that you have, which should be valid of course, can be mentioned in this question and in your answers. Please remember, during the examination no clarification will be provided. You need to make sure that all the assumptions are captured there. Nobody is going to answer any queries. You are given this question paper and you're expected to write your answers without asking for any clarification. So, what is being asked? If they are scheduled as shown below, average waiting time only is asked. We are not even bothered about what is the scheduler algorithm which is being done or being considered here. So, let us now look at this. We have, let me draw it again so that we have a better clarity on this. 0, 3, 12, 15, 18, 24. Now how many processes are here? P1, P2 come here, and then we have P3, P4, P5 at 10. So let us assume that this is 10. P3, P4, P5, they all arrive at the same time. That means what? You need to see what is the, where will they go. I told you that any process to be picked up for scheduling, that means it has to run on the CPU in the running state. It should be, prior to that, it should be in the ready state. That means they need to be in a ready queue. Okay, not in a blocked queue or any other place, because then it will not be picked up at all. It will not be considered for the scheduler. If it is a short-term scheduler which is picking up the processes to run on the CPU, it will be only looking at the ready queue. And we are showing a Gantt chart where different processes are running on the CPU. That's what we are showing. That means we are concentrating on the processes which are running on the CPU, and that means if they have to enter into the ready running state, they should have been in the ready queue. Now how they would have been ordered? Because they are picked up in this case P1, P2, and then P3, P4, P5 is given. That means they are added in the ready queue by keeping the lower PIDs in the head of the queue. That means they come into the CPU in this order. Okay. Now the question is here very simple. I don't have to explain everything, but it's all done to make sure that you understand the entire concept, not only answering this question, because this I can just explain it in 1 second. Now, average waiting time. What is the average waiting time? A process has become ready, but it is waiting for the OS to pick it up to run on the CPU. Then let us write the average waiting time in terms of processes in the increasing order of their PID numbers. So did P1 wait any time for the OS to pick it up? It came at 0 and it has picked up at 0. So the waiting time of P1 is 0. Now what about P2? P2 came at 0, okay, it came at 0, but it was given the CPU at this time. Now you may wonder whether these processes have executed completely or not. That's not under your preview of this, because this question, because only this is shown. You need to only think that, assuming that all the processes have completed the execution, and what is the waiting time, or we, because nothing is shown here, you cannot ask what is happening here. So let us concentrate on the time which is given and then understand whether was it waiting during this time? Now P2 waited for 3 seconds or 3 time units. I can't say seconds because I did not mention any time unit here. It's just a generic time unit. It could be millisecond or microsecond, whatever. So it was waiting for 3. So 0 plus 3, P2 was waiting for 3 time units. Now P2 has come. Now P3 has come at 10 and it was picked up only at 12. That means P3 was waiting for time 2 units. Now you may wonder, when the CPU was busy executing the P2, how did it even recognize P3, P4, P5 becoming ready and got into the ready queue? See, these are all background job which is done by the OS as an interrupt, timer interrupt, or it could be event driven, or any process which was maybe waiting for some unit, time unit. I have not mentioned anything prior to this. So you don't know what has happened. Our concentration is only from 0 to 24. So it could have been any other event, or the process becoming ready maybe for any reason, right? So it will be recognized, and the OS, if it is a single core also, interrupt will come, and the ISR, in the ISR routine, it would have been taken care of. So don't think that when I show that P1 is running on the CPU forever like this 15 to 18, never think that it is not interrupted in the middle. OS has every right to interrupt it. Only thing is, if it is not a preemptive scheduler, it's non-preemptive scheduler. That means here looks like the processes are running to completion. If I assume so, then it is running continuously. There are no other processes coming in between during that time. No other user processes are coming in between. That doesn't mean that no other system processes have not come. If they have come and it has been executed and come back. Okay. So we normally do not consider that as though it is a overhead, it will be done in a short duration. So we are ignoring that part of it. So as far as waiting time is concerned, when the process was not given a chance to run on the CPU is only considered. So P3 was waiting for 2. Now what about P4? P4 also came at 10 and it got a chance to run only at this time. So better to draw the picture and then understand, analyze exactly what is happening, and then write your numbers, because there is a possibility that you may think 18 means just you may write 18 or 15 time units, but it's actually not 15, because these processes did not come at 0. It came at P3 and not 10. So you have to draw the picture so that you know exactly what is, you will not make any careless mistakes when you are writing this answers. So P4 has come at 10 and got a chance to run on the CPU at 15. That means it's only time 5 time units it was waiting. What about this guy? That's 8. Okay. Because it 10 and then 18 it started running. So 8, that's all. No, you don't need to worry about when it got completed, because waiting time is the average waiting time, is the individual waiting time of all the processes. Though we have a 0 here, you have to consider that number and divide it by 5, because we want it for the all 5 processes average waiting time. So whatever is the result, you can add it up. It is going to be 18 by 5, 3.6 is the average waiting time. Okay, time minutes. I hope this is clear to you. Now there are some questions based on this particular thing, which is very interesting, and unless you have a clarity on what is happening, you will not be able to answer these questions. Now, let me read it up. From the above Gantt chart, can you give how many processes would have been in the ready queue at time unit 16? See, we are just trying to look at 16, what would have been the state of the ready queue. Now, you might wonder that I thought that P1, P2, P3 were all preempted and it did not get completed. So it was in the, it still needs to run, so it would have been in ready queue. Then you have to explain all these things and then say that ready queue, how it has been updated. A simpler assumption is to say that P1 is completed, it's done, and then P2 is picked up, because there is no time quantum unit is there, because this fixed time unit is not there. So you can assume that process have been, it's a non-preemptive scheduler, though it's not mentioned. you can say that I assume that it's a non-preemptive scheduler, and then all the processes are completed. If it is required, you can write it, or you can give the explanation that assuming that all the processes, the earlier processes have been completely done their job and exited the system at time 16, what would be in the ready queue? Then will the P4 be in the ready queue? No, because P4 is running on the CPU at time 16. So it cannot be in the ready queue during that time. What could be there is only P5, assuming that P3, P1, P2 are done. They are not in the system. Otherwise, you have to say that it is they are also there, assuming that they are not been completed and it's not mentioned in this question. So I assume that. Then in that case, the order should be taken care of. Okay, because P1 is moved and then it should have come into the P2 ready queue. Then we can say, if you say that all the other processes are also there, then you can say that P5, P1, P2, P3 are all there. P4 you cannot mention that it is in the ready queue because it can't be in the running state. At 16 it is running. It can't be in the ready queue also. So that will be a wrong answer. But my preference would be, or my suggestion would be, that you can assume that all the processes are completed, and a simpler solution would be to say that P5 only will be there in the ready queue. So that is the answer for this first question. Then there is another question. So please remember to read every line of the question. Assuming there were no other processes added to the system apart from the above five processes, give the range of time units during which maximum number of processes were in the ready queue. So now, assuming that there are no other processes, we are our life is only between the 0 to 24. How many processes were there? Maximum number of processes were there at what time units? What is the range of time units where maximum number of processes are there? I think the picture itself shows this, right? P3, P4, P5. But you can't say that at time t equal to 10, there were maximum number of processes. It's not the range. Yes, I understand that at time 10, it is there were P3, P4, P5. But I want the range of time units. Okay. So from time 10 to 12, okay, in this gap, all these processes were waiting in the queue. That's the maximum number of processes in the ready queue. What about this time unit at 15 or between 12 to 15? P3 is removed. Only P4, P5 is there. Assuming that no other process is there in the system. They are all completed. Okay. So that assumption is always holds good. And what about other time units? As the time progresses, the number of processes are going to come down. So the maximum number of processes will be there only between 10 and 12. So that's the answer for the fourth question. So this is related to the previous Gantt chart which is shown. Okay. So now before we stop this lecture, let me address this particular question and stop. Assume that you have a preemptive scheduler. Now, what I mean by preemptive scheduler, which I already explained, that there is some quantum and quantum time. That means quantum means every 2 seconds or every 2 time units or 4 time units, whatever is the time unit given, the OS gets a timer interrupt because time is maintained by the hardware timer which is running in the system with a clock fed to the timer unit. So it will keep counting 2 seconds are done, then it will interrupt the CPU. Now, when it interrupts the CPU, timer ISR will be running. Timer ISR is part of the OS. So its job is to schedule the next process apart from whatever job it needs to do. So it will forcibly take out the currently running process. It doesn't wait for the process to give up the CPU. When I say give up, either it exits or it gets blocked, then it will give up the CPU on its own, because blocked processes will be notified because OS has to take care of it. Any process waiting for some event to happen needs to take help of the OS. So OS will be notified. Then OS, once it sees that a process is in a block state, it's not going to make it run on the CPU. It is blocked for some event. It will make the state as blocked and then move it from the CPU. So you will have a context switch. That is, context switch means a process which is currently running on the CPU is going to be removed and something else is going to be brought. Will happen in a non-preemptive case when process itself is getting blocked, or it exits, or it terminates, or it does something illegal and exception is created. Otherwise, in a preemptive case, it will be forcibly taken out. Even if the process wants to run on the CPU, it will be forcibly taken out, and this context will be saved in this PCB, and it will pick up the next suitable process to run on the CPU. Now, come back. Assume that you have a preemptive scheduler that I explained what is preemptive, which was running with a quantum time units of 4. So I said 2 or 3 or something. Now let me say quantum unit of 4. That means every 4 time unit it's going to be stopped and a new process is going to be brought in. Okay. Now instead of 4, suppose you have configured a system with the 4 time units, it's configurable. I make it into 6 time units. That means every 6 time units I am going to pull out the process which is running on the CPU. Now, if I am assuming that I was running the preemptive scheduler with 4 time units, which I increased to 6 time units. Now, if the system has processes which are of much longer execution time than 6 time units, I am saying, assuming that a system has a set of processes to run, okay, all the processes that are expected to run on this system, okay, they all have a longer execution time compared to 6. You can assume much longer, maybe 100 or 200. Okay, so I am going to divide them into 6 chunks or 4, no, in the chunks of 4. Now my question is, then if the all the execution time of all of them are longer, that means I am assuming that they are not getting blocked so often. Okay, they are all running continuously. Okay, the number of context switches would reduce because of the above change. Okay, I'm saying that if I increase the quantum time where I have longer duration processes, then the context switches will reduce. Now you need to think. Suppose if I have short processes, okay, I have processes which are just taking 2 time units, okay, or maybe 1 time unit. That's all. It's done. Or it gets blocked. Okay. In that case, what happens? Now actual time unit is 6. Okay. Actual time unit is 6. Or earlier it was 4. I am making it 6. Okay. Now, if the actual execution times are shorter than even 4, what will happen? Even before the timer kicks in, the process would have given up the CPU itself. So, new process would have been scheduled. Now, the context switch is not waiting for the timer to elapse. In that case, timer is not deciding the context switch. It is the process which is deciding, because if it is of shorter duration. But if the processes are of longer duration, processes are interested in running for long, but my quantum time is blocking it, and it is picking up the process to remove from the CPU. Now when will you have more context switch, or when you will have less context switch? That you need to say. The number of context switch will reduce if I increase the time quantum units. Now imagine I have all the processes are of 100 or 200, then number of divisions that I can make are much more if it is 4. Whereas if I have the longer duration and my split is greater time unit, then number of splits that I am making is going to be less. That means whenever I am having the split, I am going to have a context switch. Now does it reduce the context switch in this context? Really, yes, right? Because when I increase the time quantum and the processes that are running in the system are much longer than this quantum time, naturally the time units that I give for the process to run on the CPU, continuous time that I give it to the particular process to run on the CPU is much more. Then I am not going to disturb the process for a longer duration. The number of context switches are going to be less. So this is the answer. But in case if the processes are of short duration, then it doesn't matter whether I increase the context switch or not, the processes are going to stop anyway. And if I have more number of short processes coming into the system, I'm going to have more context switches irrespective of whether context quantum time is kicking in or not. So you need to have a broader understanding of what is the context switch, when is it getting initiated, and how does that impact compared to the process execution time. When I say process execution time, you can assume that they run continuously for that much of time. They want to run it on the CPU. That means it's continuously a scientific process which basically has CPU burst, not the IO burst. Okay, I think It has given you a good overview of entire scheduler and the way processes are run on the CPU and how threads are created, how context switch between the process and threads are related. Now, let us meet again in the next part of the recording, taking up another set of questions. Bye bye.